finish our analog circuit completely. Okay, so today if I'll finish the unit, what I'll consider tomorrow. In the tomorrow's lecture, we'll see the problems from starting to end. We'll start from the diode circuit and we'll end our journey with the oscillations, and we'll finish the subject analog circuit. So today let me start the subject. Let me start this. So last time we were discussing about the power amplifier. Is it okay, friends? In the power amplifier, though I told you that this is not so much important, but you have to cover it because this is the part of the syllabus. As I told you last time, we got the question in 1999 from power amplifier. So this is not important unit as per the GATE exam, but they may ask the question, so you have to cover it, right? So one question we got, and the question was, this was the GATE 1987 2 marks problem, and the question was, in case of class A amplifier, the ratio of, the question is the ratio of efficiency of transformer coupled amplifier, efficiency of transformer coupled amplifier to efficiency of transformer-less amplifier. So last time we have seen for the class A amplifier in transformer coupled, the efficiency was 50%, and for transformer less, for RC coupled, we have seen the maximum efficiency was 25%, so the ratio is 2. This is 2 marks question and 15-second question, and they have given the options also. Okay, friends? So in this case, the answer is 2. I hope it's clear to you. Now I have to cover 2 more topics: 555 timer IC and multi vibrators. Okay, friends, so let me start the session. So wait a minute. So friends, the topic is multi vibrator. Multi vibrator. What is the multi vibrator? So friends, this is the regenerative circuit in which your BJT transistor or your op-amp will work in on and off state only. On state and off state. On, we can say the saturation. So in the multi-vibrator circuit, if you are using the transistor, so your transistor you are using in either off state or either saturation state. So we can say this multi-vibrator circuit are using for switching purpose only. Is it okay? Or triggering purpose? Because we are having only 2 states. Either single state or 2 state, but basically the states are saturation or cutoff. Only 2 reasons. It may be saturation or entire cutoff. Okay. So multi-vibrator, basically we have 3 types: bistable multi-vibrator. Now in the bistable we'll get 2 states and both are stable. If this is stable, after triggering to this we'll get another state, and that is again stable. Only 2 states. For any circuit we have only 2 states. One is at t equal to 0 minus. Right? Previously whatever state is there, one is that state, and another one is, suppose you are triggering this device. After triggering, again it's getting stable condition, whatever it is. So this is the bistable multi-vibrator. So it has 2 stable states. Now if I'll talk about the monostable multi-vibrator. In the monostable, we are getting only 1 stable state. See, the condition is like, suppose this is the output at the stable state of some circuit like this. After a particular point t equal to 0, suppose I'm giving triggering to it. So again it will get another condition, but this condition will be quasi-stable. Means after some time this will decay. Is it okay? So here we are having only one stable state in the monostable multivibrator. Now the most important is astable multivibrator. Astable multivibrator. Why it's astable? Because in this we don't have, for astable multivibrator, we don't have any stable state. It's totally unstable. So the condition is like this, continuously changing. No state is stable. So this is why important, because it's a square wave actually. Square wave, astable multivibrator is producing square wave like this. No state is stable. We can't say this is stable because it's changing, again changing like this. So this is the stable multivibrator. I can say this is the free running waveform. Free running square wave. Continuously changing its position. If I'll talk about the example of bistable, the best example is Schmitt trigger. Schmitt trigger. In the Schmitt trigger, we have seen only two stable states we have there, plus V set and minus V set. Okay, friends? So now if we'll see, astable multivibrator is important one. So we'll start with the astable multivibrator. Let me draw the diagram of this astable multivibrator. Okay, so why we are using multivibrator? To get condition of saturation or cutoff for very long time. Okay, because the entire concept is based on these two things only. Either it will work in saturation or cutoff. Okay, so astable multivibrator, let me draw the circuit over here. It's minus, plus, V0. It's like capacitor. This is capacitor C. Okay. Over here, I'm getting R1 and R2 grounded. That's okay, fine. And here, I have R like this. Okay, friends? Now how it's going to work? See. So we have this plus 10, minus 10, plus 10, minus 10. Okay, this is the positive feedback device. Plus 10, minus 10. So let's assume this is 5K. This is also 5K. And here the condition are either plus 10 or minus 10. Okay. Now how it works? See. Here we introduce the capacitance instead of simple V in. Let's take the output is plus 10. If this is plus 10, then this is 5 volt. This is upper triggering point or upper threshold point, UTP. Okay, so this is 5 volt. So entire thing will be over here also, because this is the negative feedbacking is also given over here. So virtual ground concept will work over here. So it's kind of this capacitor will start to charge itself. Okay, up to what level it will charge itself? I'm showing over here. This is the capacitor waveform over here, and over here I'll give the output waveform. Okay. So capacitor will start itself to charging. Up to 5 volt it will charge. Like this it will charge. This is the 5 volt. Is it okay? This is the max volt it can charge itself. If this reaches 5 volt, so the condition will become what? See, when it will become 5 volt, your output, suppose this is your output is V saturation, means plus 10. Your output is at plus 10, okay, perfectly fine. If your output is plus 10, So your capacitor will charge up to 5 volt. Once the capacitor will reach to 5 volt, now condition will become this V in, let's take it V in session, this V in point, V in become greater than UTP. Okay, upper threshold point. Then suddenly your output will drop to -10. Is it okay, friends? If your capacitor is fully charged up to 5, so this is 5 also, this is 5 also, so this is suddenly your output will get -10. Okay, it will come to -10. Now in this case, your capacitor will discharge itself up to 5 again, up to -5 it will go. This is -5. Once capacitor will reach -5, this will again become V set, and this is minus V set. Like this it will go on. So it's generating square wave. Totally unstable signal. If you are introducing capacitor over here, so your system is becoming a stable multivibrator. Is it okay, friends? This is simple schemic trigger circuit. But in the schemic trigger circuit here, we are using instead of V in capacitor. By introduction of this capacitance, we are getting a stable multivibrator. Our stable multivibrator is nothing but the square wave, free running square wave. Is it clear? Now similarly we'll see the monostable also. We have seen bistable earlier, that is schemic trigger. Now let's come to the monostable. Monostable multivibrator. Okay, so let me draw the circuit first. The circuit is, here is output, 2 resistors, let's take 5K. Here it's connected with positive terminal, like this. Here connected with capacitor. It's grounded. Over here with capacitor C, I have one diode also. In this way. This is the diode, and this terminal is grounded. And of course we are getting over here the feedback. Both feedback introduced here. This is +10. This is -10. Saturation. Okay, friends. This is trigger circuit. Okay. Trigger circuit. Now let's come to the. We are assuming that at the initial with +10 voltage here, suppose. So here the voltage drop will be 5 volt. And this will be definitely your VUTP. Definitely it will be VUTP. Now this 5 volt will come over here. Will capacitor charge now? No. Because in this case the diode is becoming forward bias. And if diode is in forward bias, so max voltage can be sustained over here is 0.7 volt only. The diode drop. So what it means? It means that, see, the circuit output is looking like, means if this is your output is continuously +10. If your output is continuously +10, so what about your input? Here I'm drawing for this. So your input wave is 0.7 only. See, over here you are getting 0.7 only. I'm drawing about this. This will maintain 0.7. Is it okay? If this is 5, the capacitor will be, because on the capacitor, our entire circuit or logic is based on the capacitor, right? In the unstable multivibrator, The capacitor was charging and discharging, and we were getting a square wave or stable multivibrator. But here, the capacitor will not charge in the positive half or in the positive plus 10. It will not charge because the diode will be in the forward bias. If diode will be in the forward bias, it will take 0.7 drop, and 0.7, the voltage can't exceed to 0.7 definitely. So capacitor will not charge in this condition. So you will getting only 0.7. Okay friends. But once we'll trigger the circuit, this entire will become 0. And because of this 0, this minus terminal or inverting terminal will become at high potential 0.7, and because of this 0.7 your V saturation will decrease to minus V saturation or minus 10. At this time, once your saturation or once your output become minus 10, so here it will be minus 5 volt. Now this diode will become in reverse bias. Now your capacitor will start to charge. At up to what point? Up to minus 5. Up to minus 5 it will charge itself. Okay friends. And after this again you will get the trigger and you will get this circuit. You will get this circuit like this. So in this case you are having monostability. Is it okay? So only one condition is stable over here. This is, and this is quasi-stable. The best example of this is coffee machine. Coffee machine. What we'll do there? We'll press that knob and we'll get the fixed amount of water into the coffee, and it again cut off. So the stable condition is cut off. And the time for which we are getting water, the hot water in our coffee mug is quasi-stable. Quasi-stable. Okay friends. So this is monostable multivibrator. Right. Now let's come to 555 timer. So this is the 555 timer. This is nothing but one IC. Okay. So let me show you that IC 555. So this IC is like over here. This is the starting of IC, as you know all. So it has 8 pins. 1, 2, 3, 4, 5, 6, 7, 8. Right? So the first is ground. The second is trigger. The third is output. The fourth is reset. These are the pin configuration. This is VC. VCC will connect to pin number 8. The 7 will be discharge. 6th will be threshold. And 5th will be control. So 555 timer is nothing but one IC having 8 pins, ground, trigger, output, reset, VCC, discharge, threshold and control. So in the examination they can ask the reset point of 555 timer IC is. So this is the pin number 4. Okay. Now let's come to the inside of it, the circuit diagram of 555 timer, and why we are calling it the 555 timer. And let me tell you one thing, this 555 timer and multivibrator, these are not the important topic as per the GATE exam, but you have to cover. So they may ask question from anywhere. Okay. So let me draw the circuit first. 555 timers. Plus, minus, here also 2-stage circuit. The output of this circuit will feed to RS flip-flop. This is Q, this is Q bar over here, and it is connected into the circuit. Now, Now this is your threshold over here. Okay, and this is the, wait a minute, three 5K registers are connected in series. That's why we are calling it 555 timer. Okay, over here 5K, this is 5K, this is over here grounded, this is discharge point, discharge, and over here one circuit, this is grounded again, this circuit is connected to this over here. Now the 555 timer, because of we are using three 5K resistors in series over here. For this op-amp circuit or comparator circuit, this is the comparator, this is the threshold, and the inverting terminal is connected over here. Perfectly fine. And for this, the non-inverting terminal is connected over here, and the inverting terminal is trigger. This is trigger. So for the first comparator, the non-inverting terminal is threshold. For the second comparator, the inverting terminal is threshold. This is connected with VCC. Okay. And over here I have reset in the circuit. This is the reset in the circuit, like this, connected over here. And this VCC is connected over here. This is the 555 timer circuit. Okay, so what's going on over here? See friends, this is the VCC you applied. What is the function of comparator? If threshold is greater than the voltage over here, let's take it VA. Here it's VB. VA and VBS. If threshold voltage, let's take VT, is greater than VA, what will happen? You will get 1 over here. Because at plus or at non-inverting terminal, this is at higher potential than this, so output of the comparator is always 1, otherwise 0. Okay. And if VA is greater than trigger, in this condition you will get output 1, and the opposite condition of this you will get output 0. Okay. This is about this comparator. Now let's come to this. If VB is greater than this triggering, so it will be definitely 1. VB is less than V trigger, so it will be 0. Is it okay, friends? So this is the simple logic. Now, based on this logic, definitely this flip-flop will work. RS flip-flop we introduced over here. So what is the characteristic table of the RS flip-flop? Let's see. R, S, Q and Q bar. 0, 0, 1, 1, 0, 1, 0, 1. Now let's take both are 0, 0. So whatever condition we have initially, after applying 0, 0, we'll get the same. So here I can write the previous state. Means whatever the condition was there, if suppose 5 was there initially at the output, and you applied, or by some means we are getting 0, 0 over here, means the condition will not change. Whatever the condition is available, it will go again. Now, if your logic is 0 and 1, so always 1 will get. Whatever the condition over here is, I don't know, but at the end you will get 1 over here. Means suppose Q is 0, suppose this is Q, or wait a minute, in the circuit let me check, it's connected with Q bar actually. So Q bar is my state, I'm considering Q bar is my state, and this is the output stage. So in this case, if Q bar is 0 and you applied 0, 1, it will become 1. You will get the 1 condition. And if 1, 0 is given, so if this is 1, it will become 0, and this is don't try. Okay, this is not defined condition is in RS flip-flop. Okay, friends. So based on this, the circuit will work when you will give 1 over here. So it will, this transistor, let's take it Q3, it will be on. When it will be on, so entire thing will discharge now. Circuit will complete, entire thing will discharge. When it will be 0, it will be in cutoff. In the cutoff region, nothing will happen. Reset will happen then. Like this, the circuit will work. Okay. So what is the main, wait a minute, let me show you. So you see first the circuits only. Okay. So we have seen the 555 timer RC. Now we can frame the schematic trigger with 555 timer also. Schematic trigger. How? We'll use the 555 timer circuit. This is the 555 timer, let's assume. Okay. And we have mean with 2 terminals only. One is trigger. This is threshold. Okay. And this one is trigger. This is trigger. Okay. Now they are connected like this. And this is connected with input Vin, grounded over here. And here potential divider circuit 100K. Over here also 100K. Connected with VCC. This is the circuit of schematic trigger. How it will work, see. Over here, if this is your Vx, so this Vx will be after dividing this VCC over here and Vin is already present. Your Vx will be Vin plus VCC by 2. Okay, this is your Vx. Now if you have Vin, let me take Vin first. Let's take Vin is sinusoidal waveform like this. Now you have to add VCC by 2. If your VCC is 10, you have to 8 plus 5. Means you are shifting your waveform. This is the 0 line and this is your Vin, suppose. So after adding VCC by 2, this 0 entire line will switch to the VCC by 2. So let me draw. Over here, this is your VCC by 2. Let's take this is 0 line. Now you shifted your input, right? Like this your input waveform will become now. Okay, wait a minute. Now, in the 555 timer, we had 3 series 5K, 5K, 5K. Is it okay? The threshold was connected at positive terminal and from here we were getting some input into the negative like this, and from here we were getting in positive feeding. Okay, so this was trigger. This was trigger, sorry. The trigger was connected over here in the lower terminal. Trigger. So what is going on over here? Here VCC. What is the voltage over here? It is 2 by 3 of VCC. Is it okay? What is the voltage here? It is 1 by 3 of VCC. The series division rule simply you can apply over here, the voltage division. So you will get 2 by 3 of VCC, 1 by 3 of VCC. Now here you connected threshold there, VT. Now if you will talk about V threshold should be greater than to this point. This point is nothing but 2 by 3 VCC. When VTH is greater than 2 by 3 of VCC, you will get